Hi everyone. I hope you've been able to stay safe, you and your family and your friends. It's good to be back with you. And I hope that you'll continue to take all necessary precautions to remain safe. So this is the way we'll be conducting lecture for the foreseeable future until we're told by the university to do anything else. And so we were last here talking about binary trees, and I want to just briefly go over that diagram again where I show the relationship between the various trees we'll talk about. So you'll recall that the set of all trees okay, and then inside there we have the set of binary trees. And inside a subset of binary trees are binary search trees. And finally, inside there's a set of self-balancing trees. So I'm just going to call that SEB or SET. And the AVL tree is one example of a self-balancing tree. Okay, so we'll take a look at these. And right now we're talking about that second circle, the binary tree. Okay, so let's see, what else can we say about this slide? Right, so we talked about the left and the right child. So a binary tree is one where each node has at most two children. And we talked about the concept of a full binary tree, which is one that's completely full. In other words, the root is at level 1, all the root's children are in the subsequent levels, and all non-leaf nodes have two children. And leaf nodes have no children at all. So this is a tree that is complete, and I drew one on the board. Let's see if we can go back and just refresh that. Okay, so if I wanted to draw something like this, is a full binary tree. Okay, you notice that every node has two children, except for the leaf nodes. They have no children. And I want to talk about the concept of a complete binary tree, which is one in which every level, except possibly the last level, is full, and the last level is filled in from left to right. So this is a complete binary tree. This is a complete binary tree, minus that little line there that showed up. Okay, so let me fill my node in. So this is a complete binary tree, but if for some reason this was not here and this is not a complete binary tree. Why? Because there's a gap right here, right? This node does not have a left child, which means we're not filling in from left to right. Primary implementation of binary trees is using pointers as you would in a list. And so this is the way that it is primarily represented. Here's an example of a node. So we see that it's implemented as a C++ struct. Its type is tree node, and it has three different data members. The first one is an integer called value, and then the second one is a tree node pointer called left, and the third one is a tree node pointer called right, and these would represent pointers to the children of this particular node. Now you'll remember that we previously asked ourselves, why would we use trees? And so it turns out that one of the main uses of trees, besides representing information that's hierarchical in nature, is to store information in a way that we can find it without having to go through all of the items in a particular list. So we previously showed that if we have a linked list and we're searching for an item or even an array, on average, we have to go through half of the items before we either find the item we're looking for or we decide that it is not present in our collection. And so if we arrange trees in a particular way, it allows us then to hopefully be able to find things in a simpler manner, and it turns out that we'll be able to do it in order log n. So if this graphic represents a tree, this particular tree is not set up in a way that helps me find the information any quicker than the linked list in A. So if I was looking for 13, I would have to basically go through the whole list or through half of the list and then decide, well, here's 13. If I was looking for 14, we're assuming this is a sorted list, so I'd have to get to node 20 before I decide that 14 is not present. And if we set this tree up in this particular way, it is no better than the linked list above it.